Last lecture in this unit, and this is the one that undermines the previous two. 3 parts today. First, measurement systems. We are going to take every number from the last two lectures and ask how much of it was the wafer and how much was the metrology. Second, 3 real fab parameters and what goes wrong when you chart them naively. Etch rate, CD overlay, each breaks a different assumption. Third, what happens when the process is being actively controlled and when there are 300 sensors instead of one. That last part is the on-ramp to the rest of this course. Today has less arithmetic than the last two classes and more judgment. The recurring theme is that the obvious thing to chart is usually the wrong thing to chart, and the fix every time is to model what you want to understand and chart what is left over. 5 things. Run and interpret a gauge R&R study and separate measurement variations from the process variation. This is a designed experiment and it takes an afternoon. Correct the capability index for gauge error and say when that correction changes the decision. Not just compute it, say it when it matters, because sometimes it doesn't. Chart the physics rather than the raw numbers. Residuals, model coefficients, spatial signatures. This is the idea that carries the middle of the lecture. Explain how SPC and run-to-run control interact and specifically what a controller hides from you. That one is genuinely counterintuitive. And describe Hoteling's T²SPE and autoencoder reconstruction error are the same idea at different levels of flexibility. If the fifth lands, the machine learning portion of this course stops looking like a new subject and starts looking like the same subject with better function approximations. 2 lectures in, here is what we have built. Lecture 1, variation sigma, the z-score and 2 kinds of error. Lecture 2, X bar, R, IMR and P charts, run rules and capability. You can take a stream of measurements and decide with a stated false alarm rate when the process changed. Now the problem. And there is an assumption underneath all of it that I have mentioned 4 times and never examined. We assume the measurements are the truth. Every sigma in the last 2 lectures, every control limit, every capability index, every part per million figure was computed from numbers produced by a metrology tool that has its own variation. We treated a CD-SEM reading as if it were the CD. It is not, and the gap is not always small. So we take that apart first, then we look at what happens when a controller is actively fighting the process, and finally at what happens when you have 300 sensors instead of 1. Before we go anywhere new, 10 slides on 4 things from last week. I'm doing this because everything today rests on them, and because 2 of them, CP and CPK, come back with completely different values by the end of the lecture. 4 ideas. The P chart, which is what you use when your data is a count rather than a measurement. CP, which asks whether the process is narrow enough to fit inside the specification. CPK, which asks the same question and adds a second one, does the process sit in the middle? And then PP and PPK, which ask both questions again over a much larger stretch of time. We spend a couple of minutes on each with a picture. If you were comfortable with the last lecture, treat this as a revision. If any of them felt like formulas you memorized, this is the version that should make them mean something. 2 kinds of data come out of a fab. Some data is a measurement. A gauge CD is 45.3 nanometers, a number on a scale, and that is what X bar R charts handle. Some data is a count. This wafer has 349 die on it, and at electrical test, each one either works or it doesn't. 17 of them failed. Each red square is a die that failed. Probe. Every pale square passed. Now turn that into one number. 17 failures divided by 349 die tested gives 0.049. That is P. The fraction that failed, 4.9%. P always lands between 0 and 1, and it is a proportion of whatever you tested. You get 1 P per lot. Plot those in time order, add a center line and limits, and you have a P chart. It is a run chart of a fraction. That P stands for proportion. That is the whole name. Here is one thing about P charts that looks strange the first time. The limits move. lot to lot, up and down, it is a staircase. The reason is on this slide. Both lots come from the same process, running at the same 5% failure rate. The left lot has 200 dies tested, the right lot has 800. With 200 die, the band is plus minus 0.046, nearly 5% points wide. With 800 die, it is plus minus 0.23, half as wide. Think about flipping a coin. 10 flips can easily give you 7 heads. 1,000 flips landing on 700 heads would be extraordinary. More trials mean the observed function sits closer to the true one. Same thing here. A big lot gives you a sharper statement about that lot, so it earns a tighter test. The staircase is the chart being honest about how much each lot actually tells you. And once the limits are drawn, you read P chart exactly the way you read every chart from the last lecture. Center line, P bar, the pooled fraction across all the lots. Here, 0.053 or about 5% of the die failing. Limits, 3 standard error either side stepping with the lot size. Points, 1 per lot in time order. Lot 16 sits at nearly 10%, well above the band. That is a signal something happened to that lot and it is worth an investigation. A detail about P bar, you compute it by pooling. The total die failed divided by total die tested across every lot. Averaging the individual lot fraction gives a different and wrong answer because it lets 200 die lot count as heavily as an 800 die lot. Different data, different arithmetic for the limit, same reading habit. Now capability. And I want to start with a picture rather than the index. 2 things are drawn here. The teal line are the specification limits. LSL, the lower specification limit, USL, the upper specification limit. A designer decided that the gate CD has to land between 43 and 47 nanometers for the transistors to work. That gives a window for 4 nanometer wide and it is handed to you. The curve is your process. It is the distribution of wafers you actually produce, and its width come from the sigma we spent so much time estimating. 6 sigma covered essentially all of it. Here 3.7 nanometers. So there are 2 widths on this slide. 4 nanometer of permission and 3.7 nanometers of its behavior. Capability is a single number that compares them. That is all it does. When the process width is comfortably smaller than that specification width, you have margins. When it is bigger, you produce crap no matter how carefully you center the process. 2 widths, 1 ratio, everything else is refinement. CP is that ratio written down. Specification width divided by process width, 4 nanometer over 6 sigma. The sigma of 1 nanometer gives 6 sigma of 6, which is wider than the 4 nanometer window. CP comes out to be 0.67 and the red areas are the wafers falling outside the spec on both sides. This process produces scrap even when it is perfectly centered because it simply does not fit. Sigma of half a nanometer gives CP of 1.33. The window is a third wider than the process, so there is margin on both sides. This is the number most fab write into contracts. Sigma of a third of a nanometer gives CP above 2, a great deal of room. Notice all these 3 curves sit exactly in the middle of the window. CP is computed from the widths alone, so it gives the same answer wherever the process happens to sit. This is what CPK adds. 2 processes identical width, sigma of half a nanometer on both panels, so CP is 1.33 for both. On the left, the process sits at 45 dead center. The distance from the mean to the nearer spec line is 2 nanometers, which is 4 sigma divided by 3 sigma, and CPK comes out at 1.33, the same as CP, which is always happens when the process is centered. On the right, the process has drifted up to 46.1. The width has not changed at all, but the distance to the upper spec line is now only 0.9 nanometers and CPK falls to 0.6. And look at what that means physically. The red area in the real wafer landing outside the specification. On the process whose CP still reads a respectable 1.33. CPK measures from the process mean to whichever spec line is closer divided by 3 sigma. It is 3 rather than 6 because you are only measuring one side. CP is about the width, CPK is about the width and the position together. The genuinely useful move is to report both numbers and look at the gap between them. When CP and CPK are close, the process is sitting in the middle, so the capability is still if the capability is still poor, the width itself is the problem, and width is expensive to fit. A better tool, a redeveloped recipe, an improved measurement system, months of work, sometimes capital. When CP is larger than CPK, the width is fine and the process has drifted off-centered. That is usually recipe offset and it is often an afternoon's work, sometimes a single number in the controller. Both situations show up as a disappointing CPK. On its own, the number cannot tell you which one you are looking at, so you would not know whether to schedule a project or make a phone call. The pair tells you immediately. So report CP and CPK together always. The difference between them is a diagnosis you get for free. Now, the same two questions asked over a different window of time. CP and CPK use sigma estimated within subgroups, the spread among 5 wafers measured in one morning, R bar over 2 D2. Here, that comes out to be 0.429 nanometers, giving CP of 1.49. That number answers, what is this process capable of while it is behaving? PP and PPK use sigma computed from all the data pulled over the whole period. Each faint curve is 1 day. The process is stable within a given day and it wanders from day to day, different materials, different lots, PM events, ambient conditions. Pull a month of it and sigma comes out at 0.62 nanometers, giving a PP of 1.08. The number answers, what did the customer actually receive? Same wafer, same measurement, 1.59 against 1.08, and the difference is everything that drifted between the subgroups. We use CP and CPK when we are improving the process. We use PP and PPK when we are making a promise to somebody. And when a supplier quotes a capability number, ask which one it is. So now all 4 on one slide. CP and CPK are short term within subgroup spread. CP asks for whether the process is narrow enough. CPK asks whether it's narrow enough and centered. PP and PPK ask those same 2 questions using every measurement over a long run, and so they include all the wandering. And here is what the number buys you, which is the part worth memorizing. A CPK of 1 leaves 1350 bat parts per million. At 1.33, it is 32 per million. At 1.67, it is 3 in 10 million. Each step is a large gain, which is why Fab cares about the second decimal place. Look at what every one of these 4 numbers has inside it. Sigma, the estimate of process spread that we built in the previous 2 lectures. Today, we ask where that sigma actually comes from. Every one of those numbers are computed from readings produced by a metrology tool, and that tool has its variation as well. By the end of this lecture, the CPK you calculated for homework will have a different value. A CDSEM report 45.3 nanometers. How much of that number is the wafer? I want an actual number. Measure the same feature again and again, you will get 45.2 or 45.4. Measure it on a different tool, you might get 45.6. Which one is the CD? 3 things I want on record before we go further. It is never all wafer. Every measurement is a true value plus a measurement error. Only question is how much and whether anybody has quantified it. It is not a small effect. On tightly tolerance parameter, gauge CD overlay thin gate oxide, the gauge is routinely 20 to 40% of the total observed variance. And it is measurable. That is the good news, and it is what makes this a solvable engineering problem than a philosophical one. A designed experiment can take an afternoon with that will separate the two. Here is the equation, the whole segment response, and you have seen it before. Observed variance equal process variance plus measurement variance. In the lecture 1, variance addition equation with two terms, variances add, standard deviations do not, same rule, new applications. Everything you have charted in the left hand side, you will never observe the process variance, you will observe the sum, and the last two lectures we have been treating that sum as if they were the process. Two consequences, both bad, and they push in opposite direction in terms of what they will cost you. The control limits are computed from the inflated sigma, so they are too wide, so you detect less than you think. Your capability index is computed from the same inflated inverse sigma, so it is too low, which means genuinely two process reports as a poor one, and you may spend real money fixing something that is not broken. One piece of vocabulary first. The gauge is the whole measurement system, not just the CDSM and the tool and the operator, the recipe, the fixture, the sample preparation all together. Gauge variation is sigma measured in the equation you will get when you measure the same wafer over and over and the answer keeps moving. Let us look at each consequence. Consequence 1, and first the word. The gauge is the whole measurement system, the tool, the operator, the recipe, the fixture, and the sample prep. Gauge variation is the sigma measurement from the previous slide, the spread you get measuring the same wafer over and over. This slide shows what that variation does to your control chart. Horizontal axis is the measurement sigma in units of process sigma. The red line is the control limit width you actually get. The dashed tail line is the width of the process alone deserves. A gauge equal to the process sigma, which sounds terrible but is not unheard of on tight measurement, widens your limit by 41%, root 2. Everything in that golden region is detection you gave away. Concretely, a shift you would have caught in 5 lots now takes 15. The chart still works, but it still has a valid false alarm. It is just substantially blunted than you believe it to be. And nothing about the chart tells you this. It looks completely normal. Consequence 2, and this is an expensive one. The process with a true CPK of 1.67, that automotive grade, is generally excellent process measured with a gauge of 0.8 process sigma reports a CPK of 1.3, which is below the standard contractual requirement of 1.33. So you fail an audit, or you launch an improvement project, or a customer requires a corrective action plan on a process that actually meets the specification comfortably. A good process measured badly reports a bad process, and the direction is always the same. Gauge error can only inflate your observed sigma, so it can only depress your observed capability. It never flatters you, which means before you accept a disappointing capability number and start spending money on the process, find out how much that sigma belongs to the measurement. Your CPK is friction when gauge eats your tolerance, and here is why it is dangerous. You cannot tell from that number itself. A CPK of 0.89 computed with a perfect gauge and CPK of 0.89 computed with a gauge consuming a third of the tolerance looks identical on the report. Same digit, same confidence, same authority. The only way to know is to have done the measurement study. So that is what measurement system analysis is, a designed experiment that lets you split the observed variance into the part that belongs to the process and the part that belongs to the abilities to see the process. It is also the difference between an engineering program that improves things and the one that chases its own instrumentation for a year. Two separate problems, and people conflate them constantly. Accuracy is whether you are on target. A biased gauge needs consistently high or low, and the shots are tightly grouped in the wrong space. Precision is whether you can repeat. An imprecise gauge scatters the shot average out to the right answer. No individual shot is reliable. And the key point is that these fail independently. A tool can be beautifully precise and badly biased, which is the third panel, or unbiased and hopelessly noisy, which is the second one. They also have different consequences, which is why we separate them. A bias cannot affect your control limit at all. A constant offset shifts the center line and points together. But it does affect your CPK because CPK depends on the distance to the spec limit. Imprecision does the opposite. It inflates your limit, depresses your CPK, different failures, different fix. Now the accuracy family, 3 systematic errors. Bias is a constant offset. Your tool reads 0.4 nanometers high on everything, found by measuring a certified reference standard, corrected by recalibration. It is an easy one. It is the known correctable number. Linearity is bias that changes across the range. Accurate on 45 nanometers, reads high at 60. This matters when one tool measures several products or several nodes, which in a high mix fab is normal. Stability is bias that changes over time, drift between calibration. And how do you detect stability problems? You measure a reference artifact every day and plot it on the control chart. That is statistical process control applied to the metrology tool. Everything from lecture to central line limits run rules applied to a gauge instead of the process. It is one of the most common real applications of the material we have covered, and it runs unattended in every fab tool in the world. Now the precision family, and this is where the gauge R&R gets its name. Repeatability, the same operator measuring the same part with the same tool several times. The scatter you get is pure equipment variation, the tool's inability to reproduce its own number. Reproducibility, the difference between the operator, tool, or days measuring same parts. Notice operator B reads systematically high on every part. That is a consistent difference between the operators. Together, those two are gauge R&R, repeatability and reproducibility. And one translation before we go on. In semiconductor fab, operator is usually not a person. CD measurement is automated. The reproducibility factor is typically the metrology tool, tool 1 versus tool 2 versus tool 3 in the fleet, or measurement recipe or day. Tool-to-tool matching is a metrology fleet. Tool-to-tool matching in a metrology feed is exactly this analysis, and it is a live concern in every fab. The standard design: 10 parts, 3 operators, 2 trial each, 60 measurements. 3 things about this design matters. The parts that span that range you actually see in production. 10 parts from 1 good lot will give you a flattering answer because part-to-part variation is the denominator in 1% of what you are about to compute. Randomize the order, or operators must not see the previous readings, otherwise you will be measuring memory, not the gauge. Each factory buys you a specific term. Repeated trials by the same operator give repeatability. Different operators on the same parts give reproducibility. Different parts give the part-to-part variation you will compare against. In the fab, substitute metrology tool or chamber for operator. The design is identical, the factor is different, the arithmetic does not change at all. Here is a real study analyzed. Repeatability: the equipment itself contributes to 0.121 square nanometer, which is 5.9% of the total variance. Reproducibility: differences between operators and tools is 0.0044 or 2.1%. Together, gauge R&R is about 0.165, which is 8% of the total variance. Part-to-part is 0.189, which is 92%. This is a healthy measurement system. The overwhelming majority of the variation you observe is real differences between parts, which is what you want. The gauge is mostly getting out of the way. Note what we are working in variances throughout, because variances add. If you convert the standard deviation, the gauge is about 28% of the total sigma, which sound much worse. Both numbers are correct. This is exactly what you must always say, which quantity you are coding. Which brings us to different percentages that people quote interchangeably and should not. Percent R&R against total variation is gauge sigma over 2 sigma. It answers, can this gauge distinguish one part from another? But look at what it depends on. Your parts. If your process improves and the parts become more similar, this percentage gets worse, which is the identical gauge. A successful improvement project makes your measurement systems look worse. Percent R&R against tolerance is 6 sigma over the specification width. It answers, can this gauge decide whether a part passes? That one is independent of the process. It depends only on the gauge and the tolerances, both of which are fixed. For disposition, deciding whether the material ships, the tolerance-based number is the one that matters, and it is the one to insist on. A gauge can look excellent on one and poor on the other. So when somebody quotes a percent R&R, always ask it every time. The two numbers can differ by a factor of 2. The conventional acceptance criteria from the Automotive Industry Measurement System Analysis Manual. Under 10% acceptable, use it. The gauge is not your problem. 10 to 30 conditional acceptable if the parameter is not critical or if a better gauge is prohibitively expensive. The important word is document. Write down why you accepted it because someone will ask it in 2 years. Over 30% unacceptable, and the gauge is substantial fraction of what you are charting. Do not interpret any capability number from the measurement until it is fixed. Below 5, which we will define at the moment, is unacceptable for a different reason. These are convention, not laws, exactly like 3 sigma. They are chosen as reasonable balance for a particular industry. 25% gauge on a non-critical upper metal layer may be a perfectly rational engineering decision. A 10% gauge on the gate CD may not be good enough. Number of distinct categories. A more intuitive way of saying the same thing. 1.41 times part sigma over gauge sigma. It estimates how many different levels your gauge can actually resolve across the range of parts you are measuring. An NDC of 2 means your very expensive CDSM is statistically present is a pass-fail gate. It can tell you big and small and nothing in between. Why 5? Why is 5 the threshold? Because below 5 categories you cannot reliably estimate within subgroup range, which means the control chart itself becomes unreliable, not just the capability number. You lose the whole apparatus, not one index. The intuition I like, it is the resolution of your measurement expressed in units of the thing you are trying to see. A ruler marked only in meters cannot chart a person's height. The ruler is perfectly accurate and it simply cannot resolve the variation you care about. 4 reasons this is harder in the fab than in the textbook. CDSM measurement damages the resist. The electron beam shrinks the feature. So your second repeat measurement is of a different smaller feature. Repeatability is confounded with the act of measuring. There are correction models for this and they are themselves the source of error. Overlay has tool induced shift. The metrology tool contributes an apparent overlay of its own. It is measured by rotating the wafer 180 degrees and remeasuring, which separates the tool's contribution from the wafers. That is a calibration step performed routinely. Scatterometry is model-based. You do not measure CD, you measure an optical spectrum and fit a model of the grating. Model error is a bias and no amount of repeat measurements will reveal it because every repeat uses the same wrong model. And many measurements are destructive. Cross-sectional seems one number per sample, so classical repeatability is impossible. You substitute the near identical parts, adjacent die, sibling wafers, and then you must argue that part-to-part similarity is good enough to stand in for a repeat. State that assumption when you report that number. Now let's go back and fix a number. Last class we computed the CPK of 0.89 on a gate CD data from a sigma hat of 0.62 nanometers, and I told you 0.89 was not acceptable. But that sigma hat came from a control chart built on CDSM measurement. It included the gauge. Suppose the gauge sigma is 0.25 nanometers, a good CDSM on a mature process. Then the true process sigma is the square root of 0.62 squared minus 0.25 squared, which is 0.57. And the CPK rises from 0.89 to 0.897. Suppose instead the gauge is 0.4, plausible on a tight feature. The true process sigma is 0.47 and the CPK is 1.16. Same wafer, same data, same measurement, and the engineering conclusion changes from the process is broken and needs a capital project to the metrologies have the problem and the better measurement recipe is the cheaper fix. So before you fund a tool upgrade, find out how much of a variance you are proposing to pay to remove actually belongs to the gauge. That question has saved more money than any technique in this course. Second part of the lecture, 3 real parameters and each one breaks a different assumption we have been making. Everything so far assumed one number per lot from a stable process measured in one dimension. Reality is messier in 3 distinct ways. Etch rate is a process that is supposed to drift. Chart alarms on the design intent, and that is a modeling problem. Critical dimension has structure inside the wafer. One number per wafer throws away the spatial signature, and the signature is where the diagnosis lives. Overlay is inherently multivariate. Translation, rotation, and magnification are different faults or different fixes, and a single magnitude cannot separate them. In all three cases, the fix is the same idea, and I'll say 3 times today, chart the physics, not the raw numbers. Case 1, etch rate. Charted the obvious way, an individual chart on the raw measurement. 14 alarms in 120 lots. And look where they cluster. Almost every one of them is a seasoning cycle, and the chamber condition over position. Over time, the etch rate falls, and then preventive maintenance resets it, and the cycle starts again. The chart is clarity reporting that the mean is not constant. That is true. It is also completely known, entirely expected, and not actionable. Nobody is going to investigate lot 88 and discover that the chamber has been seasoning. Everyone in the fab already knows it. What happens to a chart that produces 14 alarms and nobody acts on it? It gets switched off, or worse, it stays on the wall and everybody has learned to ignore it, which is the alarm fatigue failure from lecture 2 in a different costume. Let me state the mismatch precisely before it generalizes. What the chart assumes a stable mean with random scatter around it. Any sustained movement is the signal worth investigating. What the process does, etch rate falls predictably as the chamber seasons and then resets at every PM. The sawtooth is the design, not a fault. So the chart is right and useless at the same time. It is correctly reporting that the mean is not constant. That statement is true, known, and not actionable. Here is the general rule I want you to take away. Whenever a chart alarms on something you already understand, the chart is modeling the wrong quantity. It is not wrong limits, not the wrong rules, the wrong quantity. The fix is never widen the limits or switch a rule. It is to change what you are plotting. So the chart is the residual instead. Build a model of the expected seasoning curve. It is a simple version, just the average etch rate as a function of wafers since the last PM, then chart observed minus the expected. The seasoning alarms vanish because the seasoning is now a model rather than in the data. The real fault at lot 76, which was completely invisible in the raw chart but in among the sawtooth alarms, becomes obvious. Notice what changed beyond the pictures. The meaning of an alarm. On the raw chart, the alarm meant the etch rate moved, which was actually the seasoning. On the residual chart, the alarm means the etch rate departed from what we understand about it. The second statement is worth investigating, the first is not. Residual charting stated generally, because you will use this everywhere. Step 1, build a model of what you expect. It can be as simple as an average curve indexed by wafer since PM, or as complex as regression on the chamber state, incoming material, and tool history. The complexity should match what you actually understand. Step 2, chart the residual. Observed minus the expected. If your model is right, the residual is noise, and noise is exactly what a sure chart is designed for. All the assumptions we worried about in lecture 2 are most likely to hold on a residual than on the raw signal. Step 3, now the chart means something. An alarm says the process departed from what we understand about it. And notice the shape of it, the model that predicts, and a control chart on what it gets wrong. That is the entire structure of the machine learning half of this course. The model gets more sophisticated, a neural network instead of an average curve, and the chart on the residual does not change at all. Case 2, critical dimension. The problem is spatial. Two wafer maps. Left is a healthy chamber with a symmetric radial signature centered to edge variation, which is normal and expected for this tool. Right, a tilt has appeared. One side of the wafer is symmetrically different from the other. Now, identical wafer mean identical within the wafer standard deviation. Each summary statistic you would put on the control chart is the same for both wafers. Both plot at exactly the same point on your X bar chart and your R chart. No rule fires, nothing is flagged. The right hand wafer is telling you something has gone asymmetric in that chamber, gas flow, control wire, a left pin, a clamp, something with a physical location. If this feels like lecture 1's 2 data set, same histogram slide, it should. Same lesson, different axis, summarizing destroys the structure, and the structure was the signal. Let me be precise about what one number per wafer throws away. The chart sees a mean of 45.6 on both wafers and a within wafer sigma of 0.42 on both pass. The physics is completely different. Wafer A has a symmetric radial signature, wafer B has a tilt and asymmetry with the decision. So chart the signature, not the summary. Fit a simple spatial model to each wafer, an overall mean, a radial term, a tilt in X, and a tilt in Y. That is 4 coefficients from a linear fit that takes microseconds. And then pull a control chart on each coefficient. 4 charts instead of 1, and each one has a physical meaning. The radial term tracks center to edge uniformity, and the tilt term tracks asymmetry and alarm on the tilt in X points at a different mechanism than an alarm on the radial term. You have replaced one alarm that says something or with 4 charts that easily says something specific. Here is lecture 1's variance equation applied to a real CD fleet. Within the wafer, the largest single term at 39%. Chamber to chamber is 27%, chamber to wafer to wafer is 17, lot to lot is 10, and metrology 7. Where would you spend? Within wafer and the chamber matching, obviously they are together 2/3 of the variance. The chamber matching is often the cheaper of the two because it is the calibration and tune problem than a hardware problem. Now the counter example. Now consider a lot to lot at 10% and suppose you ran a project, eliminated entirely perfect lot to lot control, 0 variance. Total sigma goes from 0.96 to 0.91 nanometers. 5% on a project that eliminated the entire source of variation completely. That is a quadratic at work, and it is why the budget matters. Compute the variance budget before the project, not after. It is in the cheapest analysis in this course and it routinely redirects a year of work. Case 3, overlay, and this is the one multivariate by construction. Overlay is the misregistration between the layer you are printing and the layer underneath. It is measured at many points across each field and each wafer, and it has an X and Y component at every point. It is a vector field, not a number. And different physical faults produce different fields. A stage calibration error produces translation and everything shifted the same way. A thermal problem produces magnification. The field expands from the center. A rotational misalignment produces the rotation. The magnitude can be identical in all three. If you compute overlay magnitude across the wafer and chart that one number, you get the same value for all three faults, and they have completely different fixes: a stage calibration, a thermal investigation, and pre-alignment check. Averaging this magnitude destroys exactly the information you need to fix it. Two wafers, left vectors point outward from the center and curl, that is magnification plus rotation. Right, each vectors point the same direction with the same length, pure translation. Both wafers average about the same overlay magnitude. On a univariate chart of mean overlay, they are indistinguishable. One needs a stage calibration, the other needs a thermal investigation. Both are different teams, different tools, different days of works. And which one would you rather find out from the chart versus trial and error? So do what we did for CD, fit a model, chart the coefficient. Here is the standard linear overlay model, the displacement in X and Y at any point expressed as translation plus magnification times the position plus rotation times the perpendicular position plus higher order terms. Translation Tx and Ty. The whole field is shifted. Stage calibration, misalignment, mark detection. Magnification M. The field is scaled, thermal expansion, length heating, and wafer bow. Rotation R. The field is rotated, wafer pre-alignment and chuck rotation. Each coefficient gets its own control charge, and now each alarm points a different piece of hardware. This is the third time today we have done the same thing, model what the physics says should happen and chart the parameter of that model rather than the raw measurement. Seasoning curve, spatial signature, overlay model, same move each time. And here it is working. 3 charts, 1 per coefficient, translation in X, in control throughout, rotation in control. Magnification goes out of control at lot 36 and stays out. That is the diagnosis. Magnification out of control with translation and rotation are points directly at the thermal effects or lens heating, which is a specific investigation on a specific subsystem. Contrast that with a single mean overlay chart, which would have told you overlay is bad and handed you the whole scanner to search. The chart's diagnostic power comes from the model, not from the statistics. The statistics the same. Schwartz machinery in all 4 charts. What the 3 cases have in common? 3 statements. First, the raw number is the raw thing to chart. Etch rate drilled by design. CD has a spatial structure. Overlay is a vector field. In every case, the obvious summary destroys the signal. Second, a model turns into something chartable. A seasoning curve, a spatial fit, a linear overlay model. Each one converts physics you understand into an expectation you can subtract. Third, and then this matters, Schwartz still works. On the residuals or on the coefficients, the 1925 machinery applies unchanged. Central line, 3 sigma, run rules, all of it. Chart the physics, not the number. A model of what you expect and the control chart on the difference. I'm giving this as its own slide because it is the most transferable idea in this unit and because it scales all the way up. At the bottom of the scale, it is subtracting the average seasoning curve. Arithmetic you could do on a spreadsheet. On the top, it is a transformer trained on an unlabeled sensor trace with the threshold on the reconstruction error. Same structure, model. You can explain the chart, you cannot. What happens when the process is being actively controlled? Two different jobs, constantly confusing. Statistical process control watches. It says nothing until something changes and then raises a signal for the human. Its goal is the sentence from lecture 1. Detect a real change quickly without reacting to noise. Critically, it never touches the process. Advanced process control acts. It adjusts the recipe parameters lot to lot automatically to hold the output on target despite the drift. It changes the process continuously. Now, most treatments present this as complementary and move on. They are complementary, they also interact, and the interaction is where interesting failures live. A working controller changes your control chart can see, and it changes in a way that is genuinely counterintuitive. We will get to it in about 10 minutes, and it is the part of today I would put on an exam. 3 loops around the same process step. Feed forward. Measure something upstream, predict its effect, pre-compensate before the step runs. Incoming film thickness feeds an etch time adjustment. Resist CD feeds an exposure dose adjustment. Next, feedback or run to run. Measure the output, adjust the next lot recipe by same fraction of the error. This is a workforce for modern fabs, and as we will see, it is an EWMA in disguise. Monitoring, which is SPC. Watch everything, change nothing, raise a signal when the pattern breaks. And here is what happens in practice. Once feed forward and feedback are working well, the output looks beautiful and the monitoring loop gets neglected. Why watch something that is always on target? That instinct is exactly backwards, and the next few slides will show why. The third loop becomes more necessary when the other two are working, not less. Feed forward fast. Because it is the simpler idea. Incoming field thickness varies from lot to lot. That variation propagates through the etch and shows up as CD error. But you can measure the incoming thickness before the etch runs. So predict its effect, adjust the etch rate to compensate before the wafer goes in. Sigma drops from 1.00 to 0.37 nanometers. Almost all of the incoming variations has been cancelled. Incoming variation you can measure is variation you can cancel, which reframes metrology as an input to control rather than only a monitoring activity, and it is part of the business case for measuring more, not less. Feedback, run-to-run control. Red is an open loop, a steady drift. Chamber seasoning works the process off target over 120 lots. By the end of it, it's badly out. The teal is the same process with an EWMA controller. It is held flat lot by lot with no human involved. Sigma drops from 2.3 to 1.1. The drift has been absorbed. Notice what the controller did though. It did not remove the drift. The drift is still happening physically and the chamber is still seasoning. The controller is cancelling it lot by winding in a compensating offset. Hold the distinction. It is the entire basis of the trap I mentioned, and we'll get there in 6 slides. The EWMA controller. Almost every run-to-run controller in production is this equation. The next lot's offset equals the current offset minus lambda times the observed error. That is it. You observe how far off the target the last lot came out. You move the recipe by lambda times the amount of the opposite direction. Lambda is the whole design. Everything about the controller's behavior follows from that one number. Small lambda, sluggish, it ignores noise beautifully. A small random bubble barely moves the offset and it lets a real drift accumulate for many lots before it catches. Large lambda, twitchy, it tracks a real shift almost immediately and it chases every random bubble. And the second failure has a name for the first lecture of this unit. Chasing random wobble is tampering. Lambda equals 1 is Deming's funnel exactly. Correct the fully observed error every time and make the variance worse. The controller has a tampering knob and the lambda is it. 3 values of lambda on the same process. Lambda equals 0.1. Sluggish, look at the start. The drift gets ahead of the controller before it catches, but once it settles, the output is quiet. Lambda equals 0.3, a reasonable compromise, tracks the drift, does not chase much noise. Lambda equals 0.9, twitchy. It responds to everything including the noise, and the input variance is visibly worse than the either of the other. So there is a genuine optimum, and it is not at either extreme. Here is a trade-off as a curve, and it looks familiar. Output sigma against lambda. Too small and the drift wins. Too large, you are tampering. And the minimum sits where the drift rate meets the noise level. Look at the shape carefully. The two sides are not symmetric. The penalty of being too twitchy grows without bounds. Push lambda towards 1 and the variance keeps climbing. The penalty for being sluggish is bounded. So at worst you get the open loop behavior back. So when in doubt, err small. The sluggish controller is a controller that is not helping much. A twitchy controller is actively making things worse, and it will do so confidently. In practice, lambda between 0.1 and 0.3 covers most fab applications. And the general lesson, every controller has a tempering knob. When you are handed one, find out which parameter it is. Threading, one controller per watt exactly. A single offset for a process step is wrong the moment two products behave differently through it. Correct for product A's error and you have the same misset of recipe for product B. So you maintain a separate offset for each combination that behaves differently. Typically product times tool times chamber sometimes times the incoming layer. Each of those is a thread, and each is its own little EWMA with its own state. This creates a problem that is specific to high mix fabs. A high mix fab can have thousands of threads, many of them see a lot once a month. An EWMA with 3 observations behave like a rumor. The real solution are hierarchical. Pull information from related threads, so a thread with 3 observations borrows strength from the product family or a chamber group that it belongs to, which, if you want a bridge to the statistic you will meet later, is a random effects model, and it is one of the places where machine learning has genuinely improved the classical R2R control. 4 pieces of engineering that surround the equation, and in practice they matter more than the choice of lambda. Deadbands. Do not correct at all unless the error exceeds the threshold. This directly prevents tampering on noise at the cost of small standing offset, cheap and very effective. Maximum move. Cap how far the recipe can change in one step. Protects you against a single bad measurement driving a large confident wrong correction. Sanity limits. Absolute bounds on the recipe parameter. Controller must be able to command something physically unreasonable, so no matter what it computed. Measurement validation, reject the update entirely if the metrology reading fails its own check. Most run-to-run failures in production come from a bad measurement acted on with confidence. The controller does exactly what it is told on a number that was wrong. Control-3 is usually fine, nobody choose a bad lambda. A working controller hides the fall from you. I want to spend a moment on why this is worth a slide on its own. Every instinct says the opposite. A controller keeps the output on target, and output on target means the process is healthy. A flat control chart is a good news. All 3 of those statements are wrong in a control loop, and the reason is subtle enough that experienced engineers can get caught by it. It is the most counterintuitive interaction in this course, and yes, it is an exam question. Top chart, the CD error under run-to-run control. Beautifully in control, no points outside the limits, row run rule violations. If this were the only chart you looked at, you would sign off. Bottom chart, the controller's offset. It has been winding in a steadily growing correction since lot 60. So what is happening physically? Something on that tool has been degrading since lot 60. The controllers noticed that is its job, and it has been compensating lot by lot, so the output never moved. The fault is real, and it has been growing for 60 lots, so the output chart has said nothing the entire time. And eventually the controller runs out of range. At that point, the output goes out of spec suddenly with no warning, and a process that has been perfectly in control for months. Failure arrives as a cliff rather than as a slope you can watch approaching. Let me state the mechanism precisely, because the fix follows directly from it. The controller's job is to cancel output error. It does this job perfectly well, whether the error comes from an ordinary seasoning drift or from a developing hardware fault. It cannot tell the difference. It is not supposed to. So the fault shows up in the correction, not in the output, which means the output chart is measuring the controller's competence, not the tool's health. It is a chart of how well your control system is working, worth knowing, and a different thing from the health of the tool. So the fix, So the chart, the controller's correction signal as a process variable in its own right. It has a normal range. Under normal seasoning, offset cycles are under normal seasoning, the offset cycles predictably. A sustained trend in the offset means something is being compensated for that was not there before. In a control loop, the output tells you whether the control is working. The correction tells you what it is working against. You need both, and only one of them is usually charted. So 4 things to chart when a loop is closed. The output, as always, it confirms the loop is doing its job. Necessary and, as we have seen, no longer sufficient. The correction signal. The trends here are the fault controller is hiding. Chart it with the same run rule that you would use on anything else. Rule 4. A run on one side is one that catches a slow degradation. Headroom remaining. How close is the offset to the guardrail? The controller sitting in the 90% of its range is a scheduled surprise, and you would rather schedule it yourself. Frequency of large moves. A rising rate of near maximal correction means the process is becoming harder to hold, even if it is still being held. 3 of those 4 are free. The data already exists in the controller. It is almost never charted, and it is some of the highest value monitoring data in the fab. One more source of data, and that we go multivariate. So far, everything we have charted came from metrology, measurements on the wafer after the fact on a sample of wafers. The tool itself is also producing data continuously on every whether you look at it or not. Pressure, RF forward, reflected power, gas flows, valve position, temperature, endpoint signal. Hundreds of channels at 1 to 10 Hz for every wafer, not every lot. It is available immediately, not after the metrology queue. FDC, fault detection and classification, catches faults before the metrology ever sees them, which is a wonderful problem to have, and entirely a new statistical one. 300 correlated channels sampled continuously on a process with a legitimate step structure. Nothing we have built handles that. Here is what one sensor on one wafer actually looks like. Chamber pressure, 60 seconds. Pump down, ramp, main etch, long stable window, vent. Notice the step structure. The recipe has phases, and they are not equally informative. The pump down and the vent phases tell you about the vacuum system. The main etch window is where the wafer is actually being processed, and it is where most of the diagnosis signal lives. So if you cannot you cannot just take the mean of the whole trace. That would average the window together with the pump down, and the answer would depend mostly on how long the pump down took. Now you have to segment by recipe step first and then summarize with each step. And remember, this is one sensor. A tool streams hundreds of these per run. So here is a standard pipeline, and where it is mostly unglamorous. Segment that trace into recipe steps, summarize each window with a handful of statistics, mean, slope, range, standard deviation, and sometimes area and settling time. Then chart the summaries. And now each summary is a chartable quantity with everything from lecture 2 available. Limits, run rules, and all of it. Look at the window mean and the window standard deviation. Both shift at run 55. This is a real change in the pressure behavior during the etch, and it is visible immediately on every wafer without waiting for metrology. 2 things worth noting. Segmentation is harder than it sounds. Step boundaries move, and runs have different lengths, so you would often need dynamic time warping to align them. And you now have perhaps 20 features per sensor per step times hundreds of sensors, thousands of correlated features each run, which is exactly the situation that makes multivariate methods unavoidable. Hold that thought. One more idea before we go multivariate, and it is a good one. If sensor traces can predict the measurement, and they can because the traces are a record of what is physically happening to the wafer, then predict it for every wafer. You get a CD number on all 25 wafers instead of 3 you could afford to measure it at no metrology cost, which means tighter subgroups, faster detection, feedback from run to run controller on lots that you have never measured. All 3 are real operational gains. It is also the cleanest bridge to the machine learning half of this class. It is a supervised regression problem with an obvious business case, plenty of training data, and a well-defined target. And it is genuinely deployed. Virtual metrology for each depth, and CD is production technology in several flaps, not a research protocol. It fills in the wafer that you could not afford to measure. You still need real measurements to train it and to validate it. And there is danger. It is the one you will meet in your own projects. You are now charting the model output, and if the model degrades, the chart moves and nothing about the process changes. You have two things that can drift instead of one. And the models degrade quickly. A chamber gets clean, a sensor is replaced, a recipe is tweaked. The relationship the model learned no longer holds, and the model does not know that. It keeps predicting confidently with no indication that inputs have moved outside the domain it has been trained on. So, chart the model 2, keep measuring a small sample of real wafer, chart the prediction error against the actual measurement. That residual chart is your model health monitor. Every deployed model needs a control chart on its own residual. That is the single most transferable sentence from this course into your projects and into whatever you build afterwards. A model without a residual monitor is an unmonitored process. 300 sensors, 300 charts, 1 alarm per run. Everything we have built over the 3 lectures assume you are watching one thing at a time, one measurement, one chart, one limit. That assumption held perfectly well for gate CD from a CD-SEM. It does not survive contact with an etch tool sensor screen. And it fails in 2 separate ways, which I want to keep apart because they have different solutions. The first is multiplicity, a pure counting problem. Enough charts and something is always alarming. Second, correlation. The sensors are not independent, so a set of individually unremarkable readings can be jointly impossible. Let us take them in order. The multiplicity problem quantified. Each chart has 0.27% false alarm rate. That is fine on its own, 1 alarm per 370 points as we established in lecture 1. One chart, essentially never. 50 charts, 3% chance of at least one false alarm every given run. 330 charts, 56%. More than half of all runs will produce at least one false alarm on a process where nothing is wrong. You cannot operate like that. Nobody investigates 56% of runs, so the alarm gets ignored and you are back to alarm fatigue with a much more expansive monitoring system. Tightening each chart to compensate cost you all the sensitivity you are trying to buy. What you need is a different structure, one chart instead of 300. Multiplicity is an easy half of the problem. Here is the harder half. 2 correlated sensors. The red box is what 2 multivariate charts allow. Sensor 1 within its limits, sensor 2 within its limits. The teal ellipse is what the joint distribution actually looks like. That point sits inside both univariate limits and neither chart fires. And it is far outside the ellipse. It is in a region where the process has essentially never operated because these 2 sensors always move together, and here they have moved apart. Physically, that is often the most informative kind of fault. Pressure and throttle positions always track each other because they are coupled through a vacuum system. If they stop tracking, the couple has broken, a stuck valve, a leak, or a failed sensor. The correlation structure itself is a thing to monitor. Univariate charts by construction cannot see that. Hotel length t², a multivariate generalization of z-score. X minus mu transport times the inverse covariance matrix time x minus mu. This looks intimidating and it should not. For a single variable, it reduces exactly to x minus mu over sigma squared. It is a squared z-score. The inverse covariance matrix is doing the same job that dividing by sigma did. It generalizes measured distance in a unit of how much the data varies to many correlated dimensions at once. And that is precisely why it draws an ellipse rather than a box. It measures distance in units of how much data actually varies in the particular direction. The direction where sensors move together are cheap, direction where they normally do not are expensive. One statistic per run, one limit. The multiplicity problem disappears because there is only one chart. And note what we have done. The same z-score from week 1 generalized. Still a distance from the center measured on the unit in the units of the process's own variability. The t² chart. 12 correlated sensors, 1 line, 1 limit. The rise after run 140 is a coordinated shift across several sensors. No single sensor moved enough to break its own limit. I checked, but together they moved into a region the process cannot normally occupy. The y-axis is logarithmic, and which is conventional for t². It is a squared quantity, so it has a long tail, and a log scale makes both normal operating band and the excursion visible in one plot. The good news and the immediate limitation. one chart instead of 12, a proper false alarm, and it got something univariate charts would have missed. And it tells you absolutely nothing about which sensor is responsible. That is the next slide. Three things t² cannot. It cannot tell you which sensor. One number for everything means alarm carries no diagnostic information on its own. You get something is wrong from no pointer on a tool with 300 channels is not much better than nothing. It struggles when P is large. With hundreds of variables and limited history, the covariance matrix is poorly underestimated, and if you have fewer runs than variables, it is singular and cannot be inverted at all. You cannot invert what you cannot estimate. And it only sees behind the model. T² measures distance within a space of your training data. A genuinely new kind of behavior, a direction the process has never moved in, may barely register. The first are why PCA almost always have alongside t². The third is why SP exists. Both are the next few slides. Together they are the standard toolkit. PCA in one slide. The observation first. 300 sensors on an etch tool that are not 300 independent things. Pressure, gas, flow, throttle, position move together because they're physically coupled through vacuum system. RF forward and reflected power are coupled through the match network. The real dimensionality is far lower than sensor count. Often 5 to 20 directions account for most of the behavior. PCA find those directions ordered by how much variation each accounts for. Keep the first few and you have captured most of the behavior in a handful of numbers. Now compute t² on those few components and where the covariance is well estimated because you have far more runs than the dimensions. The second problem is from the last slide is solved. And here is the part people miss. The variation you discarded carries information of its own. It becomes a second statistic and it turns out to be a more interesting one. Two statistics, two genuinely different kinds of fault. T² asked how far along the normal direction is the run and is this an unusual amount of normal kind of variation. SPE, squared prediction error, often called Q, asks how far off the normal substrate is this run entirely. Is this kind of variation I have never seen. Look at what each one catches. Around run 140, there is a drift along a known direction. T² rises, SPE stays quiet. The tool is doing a familiar thing to an unfamiliar degree. Now around 170, something different happens. SPE jumps. The correlation structure itself has broken. Two sensors that always move together has stopped doing so. Different flaws, different statistic. You need both charts and neither is a substitute for the other. Side by side with physical interpretation because that is what makes them usable. T² inside the model. The run projects a normal direction but unusually far along them. Physically, the tool is doing a familiar thing to an unfamiliar degree. A drift, a shifted set point, a known operating mode taken too far. SP outside the model. The run does not lie in the normal subspace at all. The correlation structure has broken. Physically or something new, a sensor failed, a valve stuck, a relationship that has always held stopped holding. In practice, SPE usually fires first on the genuine novel faults precisely because the novel faults break correlation rather than exaggerating them. And I want you to hold on to SP specifically because it is the direct ancestors of autoencoder reconstruction error, same quantity, more flexible model, 4 slides away. Diagnosis, contribution plots. The idea is straightforward. Decompose the statistic back onto the original sensor. Which variable contributed most to this particular excursion? Here, sensor 5 is carrying the excursion. So that is where you start. The alarm now comes with a pointer. In practice, that is the workflow. T² or SP tells you your run is abnormal. The contribution tells you which handful of channels to look at. Then a human or increasingly unclassified trained on past events takes it from there. It is genuinely useful and it has limitations that are not always stated clearly. That is the topic of the next slide. The honest limitation, smearing. What contribution plot promises is sensor 5 caused this. Clean, actionable, and what everyone wants from a multivariate alarm. What it actually delivers is less than that. Because the sensors are correlated, a fault in one variable spreads its contribution across all the variables it's correlated with. If sensors 5 and 7 normally move together, a fault in 5 shows up partly in 7. The true culprit may not have the largest bar. It is called smearing and it is well documented and there is no complete solution. So read a contribution plot as a ranked list of where to look, not an answer. And the same caveat applies to SHAP values on a neural network for exactly the same mathematical reason. Attribution among correlated inputs is generally ambiguous, not a defect of a particular method for a property of the problem. If you are tempted to trust a feature attribution in your project, remember this slide. Beyond linear, here is the map and every row is answering Schuhart's question. Kernel PCA. PCA with a nonlinear feature map earns its complexity when the normal operating region is curved rather than flat. Dynamic PCA. PCA on a timelapse copies of the data. This is the fix for autocorrelation. The IMR problem for lecture 2 solved properly. Instead of pretending consecutive runs are independent, you build the dependence into the model. One class support vectoring machines. Learns a boundary around a normal with no distributional assumptions. Useful when the normal is a strange shape. Isolation forest. Scores anomalies by how easily a point can be separated from the rest. Handles high-dimensional mixed variable types with almost no tuning, which makes it a good first thing to try. Autoencoder. SPE with nonlinear encoder and decoders. Needs plenty of healthy data. They differ in what shape they allow normal to be. That is the only axis of the variation in this table. Let me make the autoencoder connection explicit because it is the point of the whole segment. Train a neural network to compress each run into a small representation and reconstruct it using only healthy runs as training data. Reconstruction error is the residual, it is the SPE. The healthy run reconstructs well because it resembles the training data. Novel fault reconstructs badly because the network never learned to represent that pattern. The limit is set exactly the same way we set it for SPE, a high percentile of reconstruction error distribution on healthy runs. Structurally, this is identical to PCA-based SPE. PCA projects into a linear subspace and measures what is left over. An autoencoder projects onto a nonlinear manifold and measures what is left over. Only change is that normal can now be a curved surface instead of a flat one. If you understood SPE, you already understand this, and this is why we did PCA first, not a historical interest, but because it makes modern methods transparent. Modeling the trace directly and skipping the hand design features. The 1D convolutional network learns local shape features from the raw trace, ramp, overshoot, settling behavior instead of you specifying window means and slopes. LSTM and GRUs handle variable length runs and long-range dependence, older, still competitive for modest datasets. Transformers apply the attention across the whole run, strong when you have lots of data and increasingly the default for pre-training on unlabeled traces. But here is what actually limits these projects, the labels. Fab has millions of unlabeled runs and perhaps a few hundred unconfirmed, correctly attributed faults. Supervised learning on a few hundred labels will not beat a well-tuned SP chart, which is why the winning recipe is usually self-supervised pre-training on unlabeled traces followed by anomaly detection. The label scarcity shapes the whole method choice. Evaluating a detector honestly, because this is where projects mislead themselves. Faults are rare, often well under 1% of runs. So accuracy is meaningless. A model that predicts healthy for everything scores 99% and it is worthless. You will see this reported, do not report it. Use precision and recall. Report the whole precision recall curve rather than a single operating point. Because the operating point is a choice, different users of the model make it differently. And look at the right-hand plot. Detection delay against false alarm rate. And that is the ARL trade-off from lecture 1 drawn in machine learning vocabulary. Same axis, same shape, same decision. And you are still choosing a point on the curve. Schuhart chose a point in 1924. He chose 3 sigma. You're choosing a threshold for a reconstruction error. It is the same choice with same asymmetric cost behind it. The vocabulary translate row by row. 2 communities, same concept, different words. Type 1 error is a false positive, you stopped a healthy tool. Type 2 error is a false negative, you kept making bad wafers. ARL 0 points between false alarms is 1 over the false positive rate. How often you cry wolf. ARL 1 points until detection is detection delay, how long the damage runs. Control limit is a decision threshold, the knob you choose. The contribution plot is feature attribution or SHAP. Where do I look first with the same sparing caveat on both sides? I put this line in because the two lectures barely cite each other, and you should read both. The process control literature has decades of work on detection delay and threshold economics. That anomaly detection literature keeps readers covering. If you can move between these columns fluently, you can read both, and you will notice when a paper is reinventing something. 4 problems, all real, and all of them kill projects that had good offline metrics. Concept drift, PMs, chamber rebuilds, recipe change, new products all move the definition of normal. Normal trained in March alarms constantly by August, and the process is fine. Tool and chamber matching. A model trained on a chamber A rarely transferred to chamber B without adaptation. You may need one model per chamber, which multiplies your maintenance burden by the size of the fleet or a transfer learning stream. Label scarcity. Confirmed root causes are rare and consistently recorded. And note where the labels would come from if you had them. The OCAP record from lecture 2, the signal, the finding, the action, and the outcome. That is the most valuable data set most fabs are not systematically collecting. Alarm fatigue again. A model with better recalls and worse precision than the existing chart will be switched off whether it's an AUC. The winning system is rarely the most accurate one. It is the one that engineers still trust after 6 months. Alright, so that brings us to the end of this lecture. Let me choose the unit with a whole arc on one slide. 1924, Schuhart, normal is a mean and a sigma, you chart one measurement. 1930s, run rules, normal is a mean, a sigma, and a set of patterns. You chart sequences. 1950s, EWMA and Kuzum, add a memory, you chart the accumulated evidence. 1980s, run-to-run control, normal is a target you actively hold, and as we saw, the thing worth charting becomes a correction signal. 1990s, PCA with T-squared and SPE, normal is a linear subspace, you chart the distance inside and outside it. To 2010s, autoencoder, normal is a nonlinear manifold, you chart the reconstruction error. Now, sequence model, normal is a learned distribution over the whole traces. Read down the third column, that is the only thing that changes, the shape you allow normal to be. Your model gets more flexible. The question, has this process changed, has not moved since 1924.